Okay. All right. So let's continue where we left off yesterday. This is a review slide just to bring us back on the same page. Okay. So yesterday we were talking about classical linear LDPC codes. So we have in mind a system of n physical bits. The bits can be zeros or ones, or spins. The spins will be written in this way, like sigma I z, or equivalently just capital Z, which can be plus or minus 1. The configuration space forms a vector space. This is a vector space over F2, and it has size F2 to the n, corresponding to the 2 to the n configurations. Then I'll also impose that I have M constraints. These are denoted as CA. These are, in spin language, these are certain products of spins. These are like generalized Ising constraints, if you will. These are different products of spin that are forced to be one in the code space. Okay, that's how we define the code space. These constraints can be encoded in what's called a parity check matrix. That's written here. Each row of the parity check matrix acts on some number of bits that ones label which bits it acts on. Okay, and then the row tells you that the bits appearing in that row have to have even parity. Okay. So the checks themselves form a vector space over F2 again, that's F2 to the m. These vector spaces, if you now have an m-dimensional vector representing some collection of checks, that's basically going to tell you which of these checks you're going to pick up. Okay, so these vectors denote subspaces of either bits or checks. I have k logical bits, which is my code space, is identified with F2 to the k. K is given by n minus rank of this parity check matrix. The rank of the parity check matrix tells you how many independent constraints you have. So by the time you're done imposing all of those constraints, if you have any free bits left over, those are your logical bits. Okay. So this is what we went over yesterday. And again, I'll really emphasize this way of thinking about all of these spaces in terms of vector spaces later on in this lecture. Okay. This parity check matrix can also be viewed as a linear map from subspaces or vectors that live in the configuration space to vectors that live in the space defined by the checks. Okay, so this takes in an n-dimensional vector and gives you an m-dimensional vector. So this parity check matrix is equivalently this linear map, and the kernel of the parity check matrix is the basis for your code space. Okay. So once again, we were kind of going in between this way of thinking about it from a linear algebra point of view and a Hamiltonian. Okay, so the Hamiltonian corresponding to this parity check just involves acting with products of spins in each row, and then the ground space of this Hamiltonian is my code space. Each logical X operator, which is the operator you act on to go from all 0 to some code word, defines the symmetry of this Hamiltonian. And if you have a degenerate ground state subspace, which corresponds to your code space, that can be thought of spontaneous symmetry breaking for this set of symmetries. Okay. There are some pictorial representations. Okay, so this particular parity check matrix corresponds to the 743 Hamming code, and there are some pictorial representations that are going to be useful. The first is writing your code like a hypergraph. So every bit in this code is denoted as a circle, and the bags around the circles are like generalized edges. They're basically telling you that the first check C1 acts on this collection of 4 bits. Okay? You can go from this hypergraph to what's known as a Tanner graph. A Tanner graph is a bipartite graph where one set of nodes represent the constraints or the checks in the problem. The other set of nodes represent the bits. Okay, so there's n bits, which is 7 bits here, 3 checks here, and then you draw an edge between a check and a bit if that bit is involved in the check. Okay? And finally, low density parity check, the LD, refers to the fact that this matrix is going to be sparse if I consider some family of codes where n is going to be scalar. Okay, so hopefully this is review from yesterday. Any questions on what I'm saying here? All right. Okay, So now we're going to be talking about low-density parity check codes. These are codes in which every check involves finitely many qubits or bits, and every qubit or bit is part of only finitely many checks. So this is a generalized locality condition. And a good code, okay, this is the holy grail that we're after. These are codes that transmit information with minimal overhead and with maximum robustness. These good codes are ones in which both K, which is setting the code rate, how many logical bits do you have, and D, which is the code distance, which is telling you how different your code words look, which means how robust are they. Both of these will be proportional to N in a good code. Okay, and again, in going between Hamiltonians and codes, N is my physical number of physical bits of the system size, K is log of the ground state degeneracy or the number of logical bits, and code distance is the number of flips between different ground states. Okay, so we talked about these bounds due to Bravi-Boland and Turhal yesterday, which give you trade-offs between K and D in any finite Euclidean lattice. Okay, so if you have a code which is local in a finite dimensional Euclidean lattice, then what these bounds tell you is that if you're trying to increase K, if you're trying to increase the density of logical information that you're encoding, then you have to do that at the cost of making D smaller. Okay, so you can't increase both K and D to the extent that they both scale proportionally to N. Okay, so in order for us to be able to do this, which is increase both K and D to make it proportionally to N, make them scale proportionally to N, we require expander graphs. Okay, so we're going to consider models or codes defined on more general graph geometries. And this expander graph is defined as a family of lattices or graphs where if you pick out any subset of vertices, okay, that's denoted by S here, then the number of neighbors that this subset has, as long as the subset involves less than half the total number of bits in the system, the number of neighbors that this subset has actually scales proportionally to the size of the subset. Okay, or in other words, the boundary scales proportionally to the volume in these expander graphs. Okay, what this picture is supposed to tell you is that these graphs look locally tree-like, but if this was actually a tree, then it wouldn't be an expander graph because everything that lived on the boundary of the tree would have very few neighbors, right? So what these faint links are supposed to tell you is that even though this looks locally tree-like, everything is ultimately connected up in a way that this boundary proportional to volume property holds for any subset of vertices in this graph. Okay, so those are the types of geometries we're going to be looking at. Okay, so now this is the first thing that is in review from yesterday. So we're going to talk about classical expander codes. Okay, I'm going to want to, I'll define what these are for you, and I need these expander codes. This will give me the property that I need in order to get a good classical LDPC code. Okay, so a classical code is called mu expanding if I take any configuration. So X is now supposed to be a bit string. It's a bit string of zeros and ones. This bar here refers to the Hamming weight. That's the number of non-zero identities in that bit string. And what this is telling you is that for any bit string whose weight is less than some fraction mu of the total number of bits, the syndrome, okay, how many checks that bit string triggers has to be greater than nu times n. Okay, this is the defining property of expansion. So what that's telling you is that if you start with some configuration, okay, this vector S, which is act with the parity check on the configuration, this is called the syndrome vector. Okay, each entry in this vector, remember this is an m-dimensional vector, and this is telling you how many checks are triggered by the configuration that you fed in. Okay, so if this is scaling proportionally to the system size, that tells you that you start in some code word. Suppose you start in the all zero state, which is always a code word, okay, and then you start trying to flip spins to try to get to the next code word. What this tells you is that the energy barrier that you have to go through to get from one code word to another actually scales proportionally to the number of spins that you're flipping until a finite fraction of all spins have been flipped. Okay, this is a very, very robust type of energy barrier. Okay,
contrast this with what happens in a 1D Ising model. Okay, in a 1D Ising model, you can start with the all zero or the all up state. This is a repetition code, which is a code word. Okay, and now you say that suppose you want to flip one spin. So now I'm in that configuration. This will trigger 2 checks. Okay, that's my energy cost. These two ZZ checks are going to be unhappy. That's the syndrome. But now I can keep flipping spins, so this costs energy too, all the way till I get to the all one state. Okay? So this expansion, which is a property of these linear expander codes, this gives you some very, very extreme conditions on the energy barriers that you need to overcome to go from one code word to another. Okay? So since the rate at which I'm going, I know I'm not going to get to my third lecture on spin glasses. All I want to say is this one slide on that, which is because of this expansion property. And again, this is a well-known property from things that you can show in different classical expander codes, which have been around for many decades now. Okay, using this type of expansion property, you can actually go ahead and derive some very, very striking statements about what the energy landscape looks like in these types of codes. And in particular, you can show that from expansion, the energy landscape is actually provably complex. So your landscape looks like many, many ground states. Okay, these are the code words. There's exponentially many such ground states because we have a finite code rate. These are going to be surrounded by these big, big energy barriers, okay, which make it very difficult to leave this ground state. And then not only do you have these energy barriers around ground states, but you can actually show that you have local minima at order 1 energies and at finite energy densities. You have this entire landscape with these local minima, each of which is surrounded by these very, very steep energy barriers. So this gives you this very complex energy landscape, which provably realizes a classical spin glass. And there's properties of this spin glass that are much more tractable to solve. And actually, this is also the reason in some of these papers which derived good classical codes, they simultaneously wrote down very simple decoders, local decoders for these codes. Okay, and it's because of this type of landscape that these local decoders actually work and that they're efficient. Okay, so that's all I'll say about this. But the main property that I want you to remember is this expansion property. Yeah. Yeah.
Does X to be 0, all 0?
Yeah.
How can this be satisfied?
Oh, sorry?
It just takes X.
No, it's greater than 0. All 0 is always a code word.
Did you say X?
Oh, sorry. So it's not, there's a typo. There should be mu times the Hamming weight of X. So it's scaling proportionally to how many bits you're flipping. Does that make sense? So let me write the right equation, actually. Thank you. Yeah. So if the size of X is less than mu n, then that implies that the size of the syndrome is greater than nu times the size of X. Okay, so there's a size of X on that side. Thanks. There's another hand up? Yeah.
Will this depend on your choice? You know, which basis vectors you choose for your carriage equations, or is it a property of the code itself?
It's a full property of the code itself. It's a basis independent property.
For the local decoder, is there a known error threshold for these codes?
Yeah. So there is a known, there's something called a flip decoder. It's actually really simple. It's just like zero temperature Monte Carlo. It says go in and make a local bit flip. And if it lowers your energy, then accept the flip. Okay. So as long, and that, you know, in this paper, they not only wrote down these codes, but they also wrote that decoder for the codes. Yeah. Okay. So what are some constructions of codes that satisfy this property? Okay, actually in here, let me say one more thing, which is, of course, if you have this property of expansion, then that automatically tells you that the distance of the code has to be greater than mu n, okay? Because it's telling you if you start in a code word, to get to any other code word, as long as the number of spins that you flipped is less than mu n, you have some barrier that's growing. Okay, so this tells you that the distance is, this is already giving you the good distance. Expansion implies good distance. Okay, all right. So what are some constructions of good expander codes? The first construction is a very simple one. It's from the PhD thesis of Gallagher, and he wrote this down in the 1960s, and I think it was just so far ahead of its time that it was largely forgotten for the next 20, 30 years, okay? So this is all, this is what this construction is doing. You build a regular random bipartite graph, and you treat this regular random bipartite graph as the Tanner graph, okay? So what have I drawn here? There's some number of these nodes here, which are my constraint nodes. And then there are some number of nodes here, which represent my bits, okay? What the regular refers to is that the degree of these constraint nodes, the degree of the graph there is said to be C, which is telling you that every constraint acts on C bits, okay? And likewise, the degree of these bit nodes is said to be B, which tells you that every bit is acted upon by B constraints, okay? That's what's encoded here. Apart from this, this graph is totally random, okay? So you've set C and B, but other than that, the graph is completely random. Now, you can do a quick counting. The number of edges in this graph is n times b, okay, because you have n nodes here, each with b edges coming out of it. But that's also equal to m times c, right? Because we have m variable nodes here, each with c edges coming out. Now, the rate of the code is k over n. The rate is greater than equal to the number of independent constraints that I have divided by, the rate is equal to the number of independent constraints, right? N minus the number of independent constraints divided by n. So it's greater than equal to the number of bits minus the number of constraints divided by n. Okay, so just to say this part once more. So n is the number of bits, okay? If every constraint was completely independent, so if I had m independent constraints, then k would just be n minus m. Okay, that's the number of logical bits. And then the rate would be r is k over n. But because some of these constraints might be dependent, okay, in general, all you can say is that the rate is greater than or equal to n minus m over n. But then from this equation right here, this is greater than equal to 1 minus b over c. Okay? So in particular, all you have to do is pick your bit and check degree such that c is greater than b. And if you do that, you automatically are guaranteed to have a finite rate code. Okay? So this is a finite rate code. In fact, you can show that with very high probability, this is a class of random codes, if you have to pick these graphs randomly, and you can show that with very high probability, all your checks are actually going to be independent, or there's going to be at most order 1 number of dependencies. So this rate actually approaches this target rate, and that your distance is going to be proportional to n. Okay, so I haven't proved for you that this is an expander code and the distance is proportional to n, but that's what you can do with this Gallagher construction. Okay, any questions? Yeah.
If I get a random graph,
Yeah.
can I easily check that it's good?
If you get a random graph, can you easily check that it's good? No. So actually, checking the distance of a code, you can check the rate very easily, because once you know once you know this graph and you know the parity check matrix, you just find its kernel. So that's efficient. But knowing the distance is actually an exponentially hard problem. Okay, because you need to construct every single code word, and then you need to look at the Hamming distance of that. So that's an exponentially hard problem. Yeah.
So are these codes also expanding with high probability?
Yes. Yes. These are both expanding and good. Yeah, that's right. Okay. So Then let's talk about a different construction by Sipser and Spielman. Sipser and Spielman consider what are known as Tanner codes. This is different from this Tanner graph that I just drew, but a Tanner code has two ingredients. One is an underlying graph, okay, and the other is called a small code, okay? So what you need for these codes is a sufficiently expanding, and I'll define what this means in a moment, underlying graph of some fixed degree S. This is not super important, but let's just work with that, the fixed degree part. And then you also need a sufficiently good local code, okay? And in this local code, the local code should act on n equals S numbers of bits and have some local code rate k sub L and some local code distance d sub L. Okay, so you have some underlying graph, and you're going to put the bits of your system on the edges of this graph, and then on every vertex, you're going to go in and put one of these local codes. Okay, so this is a picture that I ended with yesterday. These are two examples of these types of expander graphs. Okay, this is locally tree-like, this is a hyperbolic tessellation. So the prescription for these Tanner codes is to go in, put bits on all the edges of this graph, and then for every vertex, you have, this is a degree 7 graph, so you have 7 bits meeting at that vertex, and then you can go in and have a small code that acts on those 7 bits. Okay, so for specificity here, I've said that the small code can be this Hamming 743 code that we discussed. You can put those sets of constraints on every one of the bits in the problem. Okay, so this is like a very general kind of Tannerizing model, if you will, which lives on that kind of geometry. And notice that all your checks are local on this graph geometry. Okay, so you're working in this non-Euclidean expanding space, but once you're on this space, then everything, all the interactions are local, and everything is nice. Okay, so the LDPC condition works. Okay, and then what you can show is that if your local codes are sufficiently good, so they have sufficiently high rate and sufficiently high distance, I'll tell you what lambda 2 is in just 1 second, that tells you how expanding this graph is. So you need this underlying geometry to be sufficiently expanding, and you need the underlying small codes to be sufficiently good. And once those two properties hold, you can show that this whole, this global code as a whole is going to be both good and expanding. Okay. Now there's a little bit of a caveat here. Okay, so I've drawn these models for you because they're nice models that I can draw on degree 7 graphs with these very small codes. If you actually want to prove that graphs with these properties and small codes with these properties exist, you can do that, but the proofs generally require like really, really big examples, graphs of degrees in the hundreds, okay? So I'm not going to draw those for you, but you should just know that, this model isn't a good code, but actually, we've studied this numerically, and it reproduces a lot of the phenomenology that you can only prove for much, much more complex systems. Okay. Yeah.
So for this kind of expanding graph and this is previous random code.
Yeah.
Seems similar. They both, the NKD, they also order n.
Yes.
So what the expanding graph has some advantage, or is it very regular? I don't know.
Yeah. So in the coding literature, people kind of go back and forth between random versus explicit constructions. So things are much easier to prove for very random constructions. But you might, and that's fine, right? If you just want to prove things and you just want a code that's good, just taking a random bipartite regular graph is the easiest thing you can do. But since we want to do kind of, even in the coding literature, they're often looking for explicit examples, which is here is one code, is that good or not? That's one motivation. And the second is like, if I want to do physics with these codes, then I find it nicer to have an actual lattice that I can think about and some actual interactions instead of a completely random geometry and a random set of interactions. Yeah. Yeah.
Did you mean to say for this code, it hasn't been proven to be good?
That's it.
Right. But it might be good.
Yeah. So yes, it might be. Yeah.
You said it isn't good, but I think you meant to say it hasn't been proven.
It hasn't been proven to be good. That's correct.
Or it likely is good, right?
Well, numerics seem to suggest that it is good. but it's only numerics, and they're very, very far from the bounds that you would need to actually prove that they're good. Yeah, yeah, yeah.
Are they defined? Their goodness, how are they defined?
So for the small code, goodness doesn't really make sense in the sense that, like, I can, okay, it makes sense, but like, okay, the small code acts on a degree 7 graph, acts on 7 bits in this case, right? In general, it's going to act on some number of bits, which is the degree of the graph. The degree of the graph is always going to be finite. That's not scaling up with n. So you can pretty much choose a small code the small code doesn't have to be LDPC, it can be dense, because the small code is only acting on finitely many vertices. So you can choose a small code to be whatever you want, actually. But then once you've chosen that, the small code then has to have a good relative small code distance, okay? So this is the rate of the small code divided by s, where s is the degree, and then it should also have a good relative distance again, okay? All right. Okay, so how do you pick these underlying graphs, okay? So suppose I have a graph which is denoted by some set of vertices and some set of edges. The expansion of this graph is quantified by something called a Cheeger constant. Yeah, this is really, this is a simple idea. What this is telling you is that, again, pick subsets of vertices. As long as the size of the subset of vertices is less than 1/2, then the number of edges that are emanating from from those sets of vertices, okay, should scale proportionally to the size of the subset, okay? So basically, again, this is just telling you that the boundary and the bulk should scale similarly with each other, okay? So this is a definition of an expander in terms of the edge expansion properties. What's very commonly studied in studying expansion properties of graphs is actually a property known as spectral expansion. Okay, so if you have this graph, you can look at the adjacency matrix of the graph. The adjacency matrix is just telling you, which bits are connected to which edges. When you look at the adjacency matrix of the graph, you look at its eigenvalues. If the graph has fixed degree, you can show that the first eigenvalue is always set by the degree, and then the other eigenvalues are kind of going down are decreasing. And if you look at the gap of this adjacency matrix, which is λ2 minus λ1, then the bigger this gap, the more expanding your graph is. Okay, and in fact, you can bound this Cheeger constant by the gap of this this expander graph. Okay. There are classes of graphs known as Ramanujan graphs, which have the best spectral expansion properties. And if we want to construct such graphs, again, if you want to, you can either look at a random regular graph. These are, again, random graphs with fixed degree. These will be good expanders, again, with very high probability. Or if you want more regular constructions with no randomness, you can look at Cayley graphs of certain groups. Okay, this is like a particular type of group with some properties that you can study, and this gives you graphs of known degrees with known numbers of vertices, and you can kind of scale this up. So you can look at Cayley graphs of groups, or you can look at tilings of hyperbolic planes. Okay, and I showed you both pictures previously. So that's how you get these types of underlying geometries. And then, once you have this sufficiently expanding underlying graph, which we're now quantifying with this eigenvalue λ2, okay, or we can quantify it with this Cheeger constant, okay. Once you have that, and then if you have a sufficiently good local code, okay, so in particular, this local code should satisfy a property. I'll tell you what that is in a moment. You can basically derive, there's another typo here. This is actually just a lower bound. This is D is greater than or equal to this set of numbers here. Okay, so what am I saying here? I'm saying the rate of the global code is greater than equal to 2 times the rate of the local code minus 1. So that means that if your local code has rate greater than 1/2, you automatically have a finite bound on the rate of the global code. Okay, that's all you need to do. Select a local code with rate greater than 1/2. There's many such local codes. That automatically gives you a good rate for the global code. And now you want a local code whose distance is going to be greater than the second eigenvalue lambda2, because the distance of the global code, again, there should be a greater than equal to here, is going to be given by that set of parameters. And you see that this is only positive if your local code distance is greater than lambda2. Okay? And since lambda2 scales roughly like square root of s, and if your local code is also good and scaling roughly like s, then in some large S limit, this is basically roughly the relative local code distance squared. Okay, so that's just like a good rule of thumb. But the main point is that make your graph sufficiently expanding and make your local code sufficiently good, and then you get a global code that is both good and expanding. Okay. So now let me give you like an intuitive picture, okay, for these good classical codes. Okay, why do these standard codes give you good classical codes? Okay, so for an intuitive picture, let's look at a chunk of this graph. Once again, everything's going to be connected later. Okay, so suppose you start from a code word, so everything here is 0. Okay, and this is satisfying all my checks. Now let's flip one bit, okay, which is on this edge here. If you flip this bit, you know that your two local codes, okay, which are adjacent to that bit, you know that those get triggered. Those become unhappy, okay, because those local codes have some distance of their own, which is in this case, if I'm just thinking about this Hamming code, the distance is 3. So if you only flip one bit here, these local codes can't be unhappy, okay. So now you need to start flipping some more bits here. And then when you flip some more bits, now you flipped 3 bits, so this central code can be made happy, but then some other codes further out have become unhappy. Okay, so now you want to keep trying to flip bits, okay, and as you keep flipping bits, you make some number of checks happy, but then you kind of push this unhappiness out and you keep triggering more and more vertices. Okay, so what's going on here? The large code distance is coming from the fact, the large global code distance is coming from the fact that you start somewhere and now you need to flip many bits locally, okay, to make this local code happy. And then as you keep going out, you have to keep flipping many bits locally in order to keep your graph happy. So overall, by the time you've gotten to a global code word, you actually have had to have flipped lots and lots of bits, a finite fraction of bits throughout the graph. Okay, so that's the first point. But the second is that if your local code rate is large, that also means that you have many possibilities locally in how to make yourself happy. Okay, suppose you just had an Ising model. I know the Ising model has distance d equals n, okay, but it has only one code word. Why? Because if I flip one bit, I know that I have to flip all the other bits in order to go back to the code space. So there's only one way for the Ising model on each vertex to be happy. So as you keep propagating that out, you get many flipped bits. You get a large global distance, but you have a very small rate. So you basically want many possibilities of what to do on every vertex to become happy, so that by the time you put it all together, your global code also has a large rate. Okay, so once again, these are the conditions that if you make your local code happy and your global code, if you make your local code sufficiently good and your graph sufficiently expanding, then you can get these good global codes. Okay, so this was classical codes. We're going to now move on to quantum. Okay, but this is basically telling you that, okay, if I started with something like the 1D Ising model, which actually saturated the Bravi-Pohl interhull bound, that had k equals 1, d equals n, and the upshot of going to these expander codes is that I can get both k and d proportional to n. So this task is accomplished. I have these good classical LDPC codes. In fact, we've had them for 30 years, and I believe they're used in telecommunications and for all sorts of practical things, like even now. Okay. So now we want to move on to quantum LDPC codes. So I'm going to just briefly describe the, yeah.
Why the where the code distance scale is good. The picture that you drew basically looked like a tree, and I was wondering where the non-treeness or your expanded graphs.
Yeah, so if it was a tree, then your edges are very, your root, what are these, the leaves are very vulnerable, right? Because you can see that this leaf is only connected to this one other thing here. So you can go in and do, the size of this boundary is proportional to the size of the bulk in this expanding tree. And now you can go in and mess with things on the boundaries and destroy the properties of your code. Yeah.
Since you argue that this classic code already very good, it's very large distance
Yes.
and a lot of logical bits.
Yes.
So then it looks like we don't need to go to quantum memory. So whether quantum memory has some additional advantage or what's originally I thought the classical memory part is bad, then quantum memory is good, but now the classical memory can be really, really
No,
good.
classical memory can be very good, and the classical memory, we know it's been very good for 30 years, right? So classical codes are robust against bit flip errors, right? For quantum codes, you have a qubit, and you want to preserve some superposition of many entangled qubits. So you need it to be robust against not just bit flips, but also phase errors, phase flip, any type of error. So then you need the full kind of local indistinguishability or topological order.
I see. Quantum memory have a more requirement than classical.
Exactly. Yeah.
Just a very quick question. So the asymptotic notation n, on and on, right, for the full code, right?
Yeah.
Does this n have to be very big in the end for in practice, or do I just how small can I get away?
No, so if this, and this is an asymptotic scaling, right? You want some family of codes that you can scale up, because only then does it make sense to ask, is K and D scaling within? Like if I just give you the 743 Hamming code, right? It doesn't matter what the scaling doesn't make sense for like a 7-bit code, right? But if the Hamming code is part of a family of codes, and now you scale up the number of bits, and then you ask what the scaling does. You fix what?
To construct a practical LDPC code where I fix n equals to 50 and then
you
in
an actual experiment, that's what, there's all these papers being written about, like, I have a system of 50 qubits or 50 bits. What's the best code I can do on that? So then, you don't care so much about the scaling because the prefactor is also very important. So then you just try to optimize to get the best K and D that you can for that particular example. But here we want to think about the whole family.
I saw your code is parity check code. Why are you using 3 qubits to satisfy check?
Because this local code distance is the Hamming. Locally, I'm putting a Hamming code, and the Hamming code has distance 3. So each check here was a degree. Each check here was a 4-body check. Okay. So if I just flip one bit here, all these checks are going to be unhappy. And I need to flip at least 3 bits to get these checks to be happy again.
Another quick question. So you mentioned that this code is believed to be a good classical code. Is the part that is not proven? Which part is not being proven? Is that it seemed to me that the part for code distance is
No, I'm saying this very small example, right? Like what's proven is like, if these conditions hold, okay, then you get a global code with this good distance. This code has nk and k is 3 for this code. No, k is what? 743. Okay, yeah. So this condition is fine because it's 4/7. Okay, but this DL is not greater than λ2 in these graphs. Okay, so that's the proven part, but this is just a bound. Okay. On the distance. Like if that's true, your bound is definitely going to give you that this has got a large distance, but that bound could be very loose. So families of graphs and small codes exist which satisfy these properties. The picture that I have drawn here.
if I use that family of code, then I would guarantee to get a good cut. Then I would say it's being proved. No?
It's been proved. I'm just saying this particular model has not been proved. The Sipser-Spielman construction has been proved.
Yeah. Gotcha. Thanks.
Yeah.
Is there a qualitative difference between the two graphs that you've chosen? Because the right one has all these little cycles.
Oh, not from the point of view of Sipser and Spielman, but for some other calculations, this can matter, but not from the point of view of the Sipser-Spielman construction. Yeah. Yeah.
So you show that this good code is good for encoding and good for tracking, but it's good for error correcting. Because if there is many local ways to restore the code locally, so it seems that there is an exponentially many possibilities for possible ways to restore the code.
No, so that's a global distance is scaling proportionally to n. So you're only restoring the code locally, but then you're triggering something else a little bit further away, right? So by the time you've made everyone happy everywhere, then to get back to the code word, it's an order n difference. So that's why it's actually very good for error correction, because it means that you can have errors acting on up to a finite fraction of bits, and you can still correct it. Yeah. All right. Okay, so now let's move on to quantum codes. Okay, so quantum codes, okay, they're just going to follow much of the same type of algebra that we've developed. I'm basically always going to talk about these CSS stabilizer codes. CSS is an acronym, Calderbank, Shor, and Steen. Okay, in these types of codes, I have my parity checks. The classical parity checks now get replaced by both X and Z parity checks. So these X parity checks are just products of Pauli X operators. Now I'm just going to be working in qubit language, okay? So I have n physical qubits. These are denoted by these Pauli operators on each site. My X checks are products of X Paulis. My Z checks are products of Z Paulis. And my quantum code is a collection of these X checks and these Z checks. Okay, these X checks we'll frequently call A sub I. I is where these bits live, and these Z checks are BP. And my quantum code is going to be made up of both, and the X and the Z checks are all going to commute with each other. Okay, so there's going to be commuting stabilizer models, and the code words of this Hamiltonian is going to be the ground state space of my the code. The ground states of this Hamiltonian will form my code words. Okay. So the most well-studied example of a quantum code is, of course, the toric code, right, written by Kitaev in the 90s. And in the toric code, I'm going to draw this picture for the next, I think, 20 slides or so. Okay, so it's a square lattice with its edges identified. On some slides, I got lazy and I didn't actually color in the edges, but I'm always thinking about a torus. Okay, so that's my torus there. The qubits live on the edges of this lattice. And I have two types of checks. My X checks are these star checks living on different vertices, which act on products of these 4 X operators around each vertex. And my Z checks are these plaquette operators, which act on products of 4 Zs. Because every X and Z check overlaps on an even number of qubits, these commute with each other, and that's your toric code Hamiltonian. Okay. All right, so what does my ground state of the toric code look like? Okay, I want to make all my X and Z checks happy. So let me start with the all empty state, okay, which is all my if I work in the Z basis, all my spins are pointing up, okay? So that automatically makes the BPs happy. Now, to make the X's happy, I basically I want a +1 eigenstate of every X check. So I basically start with this empty state, and I start acting on it with the X check. Acting on it with the X check will flip spins acted on by those 4 checks, which is a loop on the dual lattice, okay? So basically, by the time I act with all possible combinations of these X checks to build up an eigenstate such that, you know, it's a +1 eigenstate of all those checks, then my ground state basically looks like a loop soup in this do a lattice, okay? So it's not just the empty state, but all possible, it's a +1 superposition of all the different loops that can exist. And this loop just means that the edges that are being crossed by that loop is down in the Z basis, okay? So that's an eigenstate. But actually, okay, the reason this has a non-trivial code space is that you don't, all your checks are not independent, okay? So let's do a quick constraint counting. My qubits are living on the edges of the lattice, okay? So suppose I have an L by L lattice. I have 2 times L squared qubits, okay? Now I have 1 X check on every vertex. So I have L squared X checks. And I have 1 Z check on every plaquette, but the number of plaquettes is the same as the number of vertices. So I have L squared Z checks, okay? So naively, you think that you have L squared X checks, L squared Z checks. Both of these have to be satisfied. So you have 2 times L squared number of constraints and 2 times L squared number of qubits. So you should have a unique ground state, okay? But on a torus, okay, this is where the periodic boundary conditions helps us. On a torus, these X checks are not all independent. If you multiply all of the different X checks, then you can see that as you wrap around the torus, every edge occurs twice. So the product of all of those X checks is 1. So you have 1 constraint on all the X checks. So you have only L squared minus 1 independent X checks. And likewise, if you multiply all the Z's, you have L squared minus 1 independent Z checks. Okay, so you have 2 L squared minus 2 constraints, which means that K equals 2. Okay, because I have L squared qubits and 2 L squared minus 2 constraints. So I have two logical qubits, which means I should have 4 ground states on a torus. Okay, to look at what these ground states are, okay, we look at these non-contractible, these ground states are labeled by these non-contractible loops. Okay, these are Wilson loops. I'll write them on just the next slide. Okay, but basically these are operators which commute with all the checks, but are not generated by any of the checks. Okay, you can verify that if you start multiplying these checks out, you'll never get something that looks like this non-contractible loop. Okay, so that those can be used to label the different ground states in the problem. So basically the ground states, which is up, 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 down, down, up, down, down, now in this logical space, is labeled by what this type of non-contractible loop is doing. And then on top of that, you add all the contractible loops that you had previously. Okay, so the way we label these ground states are by these operators, which are these Wilson loop operators. Okay, so I labeled them by these logical Z operators. Okay, these are the eigenstates of these logical Z operators. And just like in the classical code, when you act with a logical X, you flip the state of logical Z, right? So when something is completely empty, okay, which is +1 for every Z qubit, then I know that both my logical Wilson loops, okay, these are these operators here, they both have eigenvalue +1, so my logical space is up, up. Now, if I come in and I act with one of these operators here, okay, that flips a whole line of, that's what this thing is denoting, that flips a whole line of Z qubits, okay, or qubits in the Z basis, and then that's a different logical state, and you have 4 such logical states, okay? So these Wilson loops can be thought of as one-form symmetries, okay? And the fact that you have these 4 degenerate ground states labeled by the eigenvalues of these different Wilson loops, which are my logical Z's, can be thought of as one-form spontaneous symmetry breaking. Okay, and these are completely deformable because, of course, you can multiply these Wilson loops with these plaquette operators, but all you're caring about is it winding in some non-trivial way around the torus or not, okay? So the logical X's and the logical Z's have the appropriate anti-commutation relations that you would expect for Pauli operators, and the logical X's have the action of flipping what the logical Z bit is doing, okay? So now we have these macroscopically distinct ground states, macroscopic because they're distinguished by the action of this Wilson loop operator whose size is diverging as you take the system size to infinity, okay? So the distance here is square root of n, okay? Because n is a total number, and this is scaling as one linear dimension rather than the square. So the distance of this code is square root of n, and this protects against both x and z type errors, so there's locally indistinguishable corresponding to topological order. So I know this is fast, but I assume that you guys all studied this in grade school or something. All right. So okay. And what we also know is that the toric code, it's topologically ordered, and the excitations in the toric code are deconfined. There's charge type excitations. So if you start again in a system with no excitations anywhere, and you act with a string of z's, okay, what that does is it flips to charges at its ends. Or if you start in a ground state and you act with a string of x's like that, then that flips to plaquettes and it creates these plaquette excitations. But once you've created these, these strings are completely deformable, and these plaquettes these charges can be moved around at no extra cost, which is why they're called deconfined. Okay. So to summarize where we are in thinking about kind of local models on Euclidean lattices, when we were thinking about the Ising model or the classical repetition code, remember we had k equals 1 and d equals n. Now we're thinking about the 2D toric code. This is giving us k equals 2 and d going as square root of n, okay? And actually it turns out that both of these scalings, okay, for the 1D repetition code and the 2D toric code, both of these are optimal as far as this Bravi-Pull inter-Hull bound goes, okay? So that's where we've ended up. And now we want to basically straddle this gap from these good classical LDPC codes, which again have been around since the 1960s, if you count Gallagher codes, to just 2 years ago where good quantum LDPC codes were finally discovered. Okay, so there was like a long, long period where people were searching for this and not able to get there. Okay, so what's the challenge, right? Why are these so hard to construct? As I was telling you, a quantum code is basically just two classical codes. You can think of it like that, right? You have a classical code written in terms of these X checks, okay? So if you just treat that in isolation, then it's just a classical code written in the X basis. And then it has another classical code written in terms of these Z checks, okay? So in terms of this picture with these maps, you have your qubits, okay, they form a vector space here, and you have X checks which act on that vector space. So this delta 1 is the transpose of the parity check matrix, which takes you from qubits to X checks, and delta 2 is related to the parity check matrix for the Z checks, okay? So this is good. So you might ask, like, hey, we already have good classical LDPC codes. Can't I just take two good classical LDPC codes and make one of them HX and make one of them HZ and then declare victory, right? The reason you can't do that is because you need HX and HZ to commute, okay? And the same property that makes the classical code good also makes it so that you can't have commuting HX and HZ, which are simultaneously LDPC, okay? So what is that? Why is that? We need these checks to commute. In terms of these matrices, what that means is that you need these are parity check matrices. I'm writing them as these operators delta for a reason that'll become clear in a moment, but you should just think of them as either the parity check matrix or its transpose, okay, from the ones that we just talked about. But the point is that each of the Z checks okay, or each of the x checks has to commute with every one of the z checks, okay? So if you view the z checks as a classical code in its own right, that means that every one of the x checks has to label a logical operator for it, right? Because you know that if you have an x check, which is triggering 4 bits, for instance, okay, and you started in a code word of your Z code, now you know that if you act on that code word with one of these X checks, so you flip only 4 bits, you want to continue to be in the code space, right? But this would then give you a logical operator because you know that the code is LDPC, because you know that your X checks are going to be acting on at most order 1 numbers of sites. This would tell you that HZ actually has to have very, very small distance. It has to have order 1 distance, right? So if you picked your HZ and HX to both be good, then you cannot both make them LDPC and satisfy this property, okay? So there has to be some extra structure that you need to add to get these types of quantum codes. Now, it turns out that the extra structure that you have to add is already hidden in what's there in this slide, okay? What the slide is telling you is that you need 3 different vector spaces, okay, labeling the z checks, qubits, and x checks, with maps between these vector spaces. And the maps have to satisfy the property that the composition of these 2 subsequent maps should give me 0 mod 2. Okay, that's the structure that I need for any quantum CSS code. This structure turns out to be mathematically identical to what's called a 2-dimensional chain complex. Okay, so the name of the game with these product constructions that are being used to construct quantum codes out of classical codes is to start with classical codes. You can view them as level 1 or 1-dimensional chain complex. A classical code just needs bits and checks, but then you need to compose them in a way to build up an algebraic structure which is higher dimensional in some sense. Okay, and I'll go through this in a lot of detail now. Okay, so I just want to flag these 2 abstracts from these papers that recently constructed these codes. Okay, and what they're saying is, just the first line here, we construct classical and quantum LDPC codes obtained by the lifted product construction over non-abelian groups. Okay, so a key element in these papers is a product construction, and over the rest of today's lecture and tomorrow, I want to kind of tell you what that looks like. Okay, and in the second paper, the first paragraph should actually make sense to you now. It says Tanner codes are long error-correcting codes obtained from short codes and a graph with bits on the edges and parity check constraints from the short codes enforced at the vertices of the graph. Combining good short codes together with a spectral expander graph yields the celebrated expander codes of Sipser and Spielman, which are asymptotically good classical LDPC codes. Okay, so this is what we went through right now. And now, basically, they want to construct a different kind of graph, which is going to come from some product of graphs, and then use those to obtain these 2 classical codes that will together define a quantum code. Because we want to unpack some of these product constructions now. So this is what we're trying to do. We're going to take these 1D chain complexes or these 1D good classical codes. We're going to take a particular kind of product. I'm going to describe the simplest product to you first, but then there's a special kind of product that you need to take to get a very abstract kind of higher dimensional chain complex for these codes. Okay, and really the picture that you should have in mind is that for this quantum code, you're trying to construct something like a 2D manifold. Okay, you don't have topological order in 1 dimension. You need 2 dimensions for it. Okay, so the way you should think of this roughly is building up a higher dimensional manifold, but it's going to be a very abstract manifold by taking products of 2 lower dimensional manifolds. Okay, so you can take a product of 2 circles and build a torus out of it, and this is going to be a very, very souped up version of something like that. Okay, so now we're going to start with a very, very simple description of these chain complex and homology theory. okay, because this really is a unified description of all CSS stabilizer codes. Okay, it's a very, very powerful language. Most of you know, or you can go and learn tonight, the toric code very well. But once you think of the toric code in this language of homology theory, you actually know all CSS codes. It doesn't matter if they're fractons or toric codes in 2D, 3D, 4D. It really doesn't matter. All of them have the same kind of structure. Okay, so, and whether the graph is Euclidean or not, all of that is going to be one unified description. And the point is that the code that we'll talk about how this works, but the code is going to define a notion of geometry on its own. And this notion could actually be quite different from the underlying geometry on which the physical bits and qubits live. Okay, so even though, like, you know, the toric code lives in 2 dimensions, Haas code lives in 3 dimensions, these good classical LDPC codes live in expander graphs, which are infinite dimensions. The physical lattice is very different, but they're all going to be 2-dimensional chain complexes. Okay, and that's going to be the relevant feature of them. That's important. Okay, so what's a chain complex? A chain complex is a sequence of vector spaces, okay, V0, V1, V2, with boundary maps or linear maps. You should just think of this as a map between 2 vector spaces between these. Okay, and this is slightly idiosyncratic notation. I like to call this the dimension of the chain complex, just to remind myself of like physical dimension. Okay, so this DC is going to be how many such layers exist in this chain complex. And I'm going to draw a lot of pictures, so I just want to set the equation, then I'll be drawing many pictures. So what this condition, a chain complex, is defined by vector spaces and maps, and the maps have to obey that the composition of 2 subsequent maps is going to be 0, okay? Which colloquially means that the boundary of a boundary is 0. And this homology theory is basically going to be a combination of topology and group theory, okay? But we're going to do the very baby version of it. Since we're only talking about bits and qubits, we only need to look at the group. For us will just be F2 or Z2, if you want to think of plus and minus 1. And for topology, I'm actually going to start with what all of this looks like for an actual physical Euclidean manifold. Okay, so suppose I actually have 2D space. I want to define a cellulation of this space. So what is a cellulation? Okay, and then I'm going to first define a cellulation, and then I'm going to put some elements of a group on that cellulation. Okay, that's going to be the name of the game. So what's a cellulation? Let me take a 2-dimensional manifold. Okay, that's what this plane here, and divide it up into cells of dimension 2. Okay, so those are my 2 cells, which are plaquettes. 1 cells are dimension 1 objects. In this case, when 2 plaquettes meet, they define an edge or a 1 cell. And 0 cells are vertices. When 2 edges meet, they meet at a 0 cell, which is a vertex. Okay. These cells define what are called, these n cells, 0, 2, 1, and 2, define n chains. Okay? So what's an n chain? An n chain just means go in. So here I'm drawing for you a 2 chain. 2 cells are plaquettes. Okay? So go in on every plaquette and assign a group element which is either 0 or 1. Okay? This will form all such assignations form a vector space V2. Okay? So again, remember what we were doing earlier when we first started. Okay? We had bits and checks and code words, and all of those were forming vector spaces. Okay? So that's what you should keep in mind. That's where we're going to be headed. Here, I have a series of objects which are plaquettes, and on those series of objects which are plaquettes, I can put down bits which are 0s and 1s. And now, basically, you should treat every plaquette as a basis vector, okay? And a configuration is going to be, for every plaquette, just label as a 0, 1. This whole thing is a vector, okay? The vector addition is mod 2, and the identity is a 0 vector, okay? So all such 2 chains will form a linear vector space V2, with the field F2 here. Okay. I can do this likewise, okay, and I'm going to use this coloring where if something, the color isn't showing up, is it? Okay, so the ones were supposed to be colored. We'll see how much that messes me up later. Okay, so likewise, a one chain means that treat every edge as a basis vector, okay, and now you can add the group element, which is 1 or 0, and every such configuration is going to define a vector for you, and all these configurations will form a vector space V1. Okay. And finally, I can do the same for my vertices, which define a 0 chain and the vector space V0. Okay. All right. So now the boundary maps, okay, these are just linear maps from n chains to n minus 1 chains. So I have this plaquette, okay. If I act with the map delta 2 on this plaquette, what it should return, okay, so this is a vector, okay, the vector is 0, 0, 0, 0, 1, 0, 0, so zeros everywhere except on that one cell. This can be viewed as a F2 or Z2 valued matrix. When you act with this matrix on this vector, what you get is a different vector. This vector now lives in the space for which every basis entry is an edge, and what it returns is a configuration with 4 ones, okay? So there's a 1 on this edge, and that edge, okay? So it basically does exactly what you would think pictorially, takes me from that plaquette to a collection of 4 edges. This is a linear map, so if I act on it with 2 plaquettes, okay, it's basically going to give me that collection of 4 edges and this collection of 4 edges, but then I'll add those 2 vectors mod 2, and because I'm adding them mod 2, this edge gets counted twice, so it's no longer, it's not there, okay? So that's why it's again pictorially, if that's your plaquette and you want the boundary map to return the boundary, well, that's the boundary you would have drawn, right? I'm going to this algebraic structure in addition to the pictures, because by the time you're doing very abstract spaces, you're going to rely on the algebra and not the pictures. But so that's why it's just useful to keep both in mind. Yeah.
Is mod 2 or because they are opposite, have opposite direction?
No, right now they're just using mod 2. There's no orientation on this. Nothing is oriented. Like every entry on my, it's just zeros and ones. It's just, I'm just doing F2, right? So every plaquette is either 0 or 1, every edge is either 0 or 1. If you're doing U1, you can start doing orientable things, but I'm not doing any of that. Yeah, you can put different,
simplify.
You can put different groups, and then that will lead to more structure. I'm just doing Z2, so there's no orientation. It's either on or off. Yeah.
Here you are dealing with quantum code. You are thinking you want to deal with quantum code, not classical code, right? Just make sure.
I'm not dealing with codes right now. I'm just doing homology right now. So I have a manifold. I have plaquette-like objects, edge-like objects, vertex-like objects, and then I'm going to add zeros and ones to them, which are the entries of my group, and I'm going to tell you that there are maps which take you from one to the other. I'm going to relate it to codes in a moment.
But you are aiming to deal with quantum code. But you are thinking about the n-chain associated with some vector space over a field.
Yes.
Thinking about Hilbert space.
Yes. Yeah, that's right. Okay. So likewise, if I look at the boundary map applied to this edge, I get these 2 vertices. And if I look at the boundary map applied to these 2 edges, then I get those 2 vertices there. And again, this one doesn't enter because this is counted twice modulo 2. Okay. So now you can easily see this chain complex. This is, if I start from a plaquette, I act with this boundary map, I get four edges, and I act with the boundary map again. And now every vertex that was part of those 4 edges is counted twice. So this boundary map takes me from an element of a 2 chain, a 2 chain, which is an element of V2, to a 1 chain, which is an element of V2, to a V1, to a 0 chain, which is element of V0. And then the composition of both of these maps gives me 0 mod 2, which is just boundary of boundary is 0. Okay? So we can talk about a couple of more, there's just going to be two more concepts that I'm going to introduce, and then we can understand all of the toric code in this language. Can I get 10 minutes? Is that okay? All right. So an n boundary group, okay? So this is an element of B1. So Bn, which lives in Vn, is the set of n chains, which are boundaries of n plus 1 chains, okay? So an n plus 1 chain, here if I'm talking about B1, a B2 chain is a set of plaquettes. So this is a collection of edges, which is a boundary of a plaquette, okay? So that's why this is a boundary chain, and the set of all boundary chains forms a subgroup of the full group. Likewise, you can talk about a cycle group, okay? A cycle group is a set, an n cycle group is a set of n chains which have no boundary, okay? So if I look at this collection of edges and I act with the boundary operator on it, as we saw, you know, each vertex that will get returned is counted twice, so this has no boundary. And likewise, if you have a non-contractible cycle here, okay, that again has no boundary. Yes? V3? So right, so for this, there is no V3. I'm just talking about V0, V1, V2. If you were working in 3 dimensions or 3 effective dimensions, then V3 would be cubes. And then V4 would be higher dimensional cubes and so on. That's right. So the point is that every boundary is a cycle, but not every cycle is a boundary, okay? This is a pictorial representation, okay, of something that I mentioned there about redundancies. If you want to know about cycles in C2, then this is a collection of plaquettes for which has no boundary. Okay, so if I start with 1 plaquette, that has a boundary corresponding to 4 edges, but I need to multiply out all the plaquettes on a system with closed periodic boundary conditions in order to get something which is a cycle in the plaquette space, okay? Because this is something, it's a collection of plaquettes which has no boundary, okay? So in this language, homological equivalence is again very easy to understand pictorially. It's basically just telling you that 2 chains are homologically equivalent if they're equivalent up to the addition of some boundary, okay? So this chain here, which is this winding object, is equal to this cycle, which is non-trivial, plus this trivial boundary. So this first homology group is defined by cycles mod boundaries, and on a torus, and my colors are not showing up too well. On a torus, there are 4 equivalence classes, basically given by these. There's no non-contractible loop here. There's 1 there. There's 1 there, and then there's 2 here. So it's isomorphic to Z2 times Z2. Okay. So hopefully all the structure of the toric code is becoming somewhat apparent. Okay. So now let's just revisit the toric code in this language. The point is that once I've defined this cellulation, okay, and I can define this cellulation for in any way I want. I can work with a honeycomb lattice, okay? I can change how I cellulate things, but I'm going to define my qubits on 1 cells or edges. That's what each of these boxes are. My Z operators, I'm going to define these to live on 1 chains, okay? So I'm going to say that anytime you want to act with Z on some collection of edges, then that collection of edges defines a 1 chain, okay? Now you can easily see what charges look like. If you act with a collection of Z's on these two links, you trigger a charge here and a charge here, okay? But this is just the boundary, right? It's just a 0. These are vertex operators, which are the boundaries of 1 chains, and those correspond to charge syndromes in the toric code. B1, okay, B1 is 1 chains which are boundaries. So these are all collections of edges which are obtained as the boundaries of plaquettes. So you can see that this is the subgroup generated by all the Z stabilizers, okay? So a Z stabilizer is a plaquette. When you act with that, that plaquette picks out 4 edges, okay? That's a boundary of the plaquette. And as you keep multiplying plaquettes, that generates your entire Z stabilizer group, but that stabilizer group is exactly defined by B1, okay? Because the B1 is a set of all edges which live on the boundaries of plaquette-like objects, and the plaquette-like objects are exactly my Z checks, okay? Any cycle, C1, by definition, okay, because it's a cycle, it doesn't trigger, it has no boundary. So a cycle does not trigger any vertex operators. So cycles commute with all vertex operators. So there are some cycles which are trivial, like this, which are boundaries, and then there are other non-trivial cycles. So this first homology group, which is these non-trivial cycles, these define your logical Z operators, okay? So my Z operators are living on 1 chains, and these non-trivial cycles define these logical Zs. So homological equivalence now means that the action on the code space is invariant to multiplying with Z stabilizers, okay? Because when you multiply with Z stabilizers, you get these different boundary, these B1s, but then as we showed, like if you have some non-trivial cycle and you multiply those with boundary operators, those are all homologically equivalent, okay? So this basically explains everything about the Z portion of the toric code in this language of homology, okay? So what about X? Well, to do that, you just look at this dual cohomology, okay? So basically, cohomology is to homology like bras are to kets. If you take a vector from the cohomology group and you act on it with a vector from the homology group, you get back a number, okay? So if you take co-n chain, and this is like a kind of inner product between a co-n chain and an n chain, then you should get F2. So basically, again, in 2D, it's easy to visualize. You just look at the dual lattice. And now, working on the dual lattice, you can once again define co-chains, co-boundaries, co-cycles, co-homological equivalences in exactly the same way. Here, it's very easy to see because this is just a square lattice again. So everything that we did for the Z's, you can now do for the X's, okay? And basically, this inner product is going to be the number of crossings mod 2 between a chain and a cochain, okay? So here you can see that the chain lives in the direct lattice. That's this collection of 2 blue edges. The cochain lives in the dual lattice, and because these cross ones, you get this is equal to 1, okay? Whereas if you wrap these around and made them into loops and they cross twice, then that would be 0. So now we're almost done. The point is that, you know, all your qubits which live on edges, you have chains that go through those edges on the direct lattice, and you have cochains that go through those edges in the dual lattice. And you basically say that all your Z operators, anytime you want a string of Z's, those are going to live on 1 chains. Your X operators are going to live on co-1 chains, and all your commutation relations are fully encoded with this inner product, okay? So if you have some collection of edges denoting where Z acts, and a collection of dual edges denoting where X acts, then basically the operator strings with the Z and X, they either commute or anti-commute, depending on whether the number of crossings there is even or odd. Okay, so the commutation relations are also encoded homologically. All right, so this is now the entire structure of the toric code understood in this way. And what we're going to focus on next time is how, even when you don't have the crutch, okay, so here, the nice thing was that I had an actual 2D lattice. That actual 2D space, I could cellulate it and I could get a notion of plaquettes, vertices, edges, okay? And the plaquettes, vertices, edges of the actual 2D space also corresponded to the plaquette-like objects, which are my Z checks, my vertex-like objects, which are my X checks, and the qubits, which live on edge-like objects, okay? You can do this much more generally, and when you do it much more generally, the actual cellulation of whichever manifold you're talking about may not agree with the objects that you're going to associate with x checks, z checks, and vertices, but there's still going to be, but the main point is that as long as you have this two-dimensional chain complex, all the structure that we've understood from the toric code, if you put x checks, z checks, and qubits at the right places, all of that structure will basically carry forward. Okay, so I want to do one last thing, and then we'll end. Okay, so we revisited the toric code in this language. You can actually also revisit the 2D Ising model in this language. In the 2D Ising model, your bits are now going to live on your 0 cells, which are vertices. Z operators, okay, the operators have to act on the bits, so they're going to live on my 0 chains, okay? But basically, these 0 chains are the boundaries of 1 chains, which correspond to collections of Z stabilizers. Z stabilizers are just Ising interactions, which are ZZ interactions. So you take a collection of ZZ interactions, and you see what's left, and that's where your action acts. And now, cycles, okay, cycles here are redundancies of Z checks, okay? If you have a cycle that's telling you that that's a product of Z checks, which is not triggering, which is not acting on any vertex, okay? So that's a product of Z checks, which is just going to give me the identity, which means that there are linear dependencies between my Z checks, okay? So the upshot is that when you have this sequence of, and this we'll pick up here next time, basically when you have this two-dimensional chain complex defined by these boundary maps satisfying this property that defines for you plaquette-like, edge-like, and vertex-like objects, you can put a quantum code on it where you put x checks on the vertices, qubits on the edges, and plaquettes on the z checks on the plaquettes. But you can also put 2 classical codes on the same chain complex where you'll now put bits on the vertices or on the plaquettes. You put checks on the edges or the dual edges. And now the fact that this third layer exists in your manifold, okay, there's a big difference between the 1D Ising model and the 2D Ising model from a physical perspective. And that comes from the nature of these redundancies. The fact that this third layer exists means that you have redundancies among your Ising checks, which means that if you take a product of 4 Ising checks around some plaquette or dual plaquette, you know that you're going to get 1. And it's exactly these classical codes, which you can define on the chain complex, which when you gauge, you get the quantum model, okay? So basically, a chain complex simultaneously defines 2 classical codes and a quantum code, and these are related by gauging. Yeah? And the point is that these bits, checks, redundancies, they themselves now define this notion of geometry. I've put hyper edges and hyper plaquettes because a check doesn't have to act on just 2 bits, right? We saw checks that acted on 4 bits. So this is not really an actual edge in some geometry, but it's like it acts like an edge because it defines this notion of geometry, which can be distinct from the geometry of the graph. And I'll just the point is that the importance of these physical lattices, such as dimension, the 1D Ising model and the 2D Ising model act very differently. This is well appreciated in condensed matter, but this code geometry is actually just as important. Okay, so here are some examples where in this case, my code geometry and the physical geometry are the same. I just put the 1D Ising model on, I put my bits on the vertices and checks on the edges, and then my plaquettes define my redundancies. But actually, there are other types of Ising models which have been studied in fractons, where the actual model itself might live in 3 dimensions, but there are no local redundancies, so it actually morally looks like it's actually this 2-dimensional model morally looks 1D, and this 3D model morally looks 2D. So I'll pick up here next time. But let me stop now.